Hey, glad you could join us. Seriously, thanks for making time to drift through the stars with me. Whether you're curled up on the couch, tucked under a blanket, or just letting your mind wander as you listen, I'm happy you're here. Out here, things move slower, or faster, or, well, that's what we're figuring out. You'll see what I mean. Thanks for being here. If you like listening to quiet stories about space and stars, please tap the like button. It helps others find this peaceful place too. And if you want to come back for more calm journeys through the universe, please like and subscribe. Enjoy what I do here, and let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Hey everyone, today we're looking into stars. But not just any stars. We're slipping through time, brushing past suns that burn blue and white, red and gold, and asking one curious question: how does time pass out here? Now, if you're sitting somewhere with gravity holding your socks on, time probably feels pretty normal. 1 minute ticks into the next, your tea cools, and the cat eventually gives up knocking things off the table. But in space, time isn't quite so steady. It bends, it stretches. Sometimes it slows to a crawl. Other times, it races ahead and leaves you blinking behind. Let's ease forward now, slowly, past the edge of Earth's atmosphere. Look down, see how our little blue home glows softly under a curved veil of clouds. The sun is kissing the oceans below, light slipping sideways into orange. That's time too. Not just movement, not just moments, but the way light takes its sweet time getting anywhere. Already, even this sunlight is 8 minutes old by the time it hits your cheek. Feel that? Now drift beside me and let your breath settle. We're not pushing. There's no up here, no down either. Just the easy hush of nothing at all. And in that nothing, time gets curious. Picture yourself beside a black hole. Not too close, don't worry. Just near enough to feel the odd pull. The stars around you seem to stretch. Light slows. If you had a wristwatch floating there on your arm like a slow jellyfish, you'd notice it ticking differently than it would on Earth. That's gravitational time dilation. But forget the name, just feel the effect. Imagine waving to a friend far away, and when they wave back, the motion takes longer to reach you. Their voice, when it comes, is deeper, drawn out. It's not them slowing down. It's the space between you and the black hole that's stretching time like warm toffee. You and I? We're floating just outside that mess, safely. But if you dipped closer, your seconds would stretch compared to mine. You could spend a week there, then fly back and find 100 years had passed. Think of that. Your garden would be overgrown. Your favorite show would have had 17 spin-offs. Someone might have finally invented a decent space coffee. And still, you'd feel like no time passed at all. Let's drift on. See that star blinking ahead? That's a pulsar, a little spinning corpse of a star, sending beams out like a lighthouse. Every blink is precise, ticking like a galactic metronome. Now, that's a clock you can trust, but even those can bend time's rules. If one of these got close to something heavy, like a neutron star or a black hole, the pulses would change. Time would stutter. You might notice how quiet it is out here. Not silent, just still. The kind of still that lets you hear your own heartbeat. The kind of still that hums in your bones if you let it. Space doesn't rush. It drifts. It waits. And sometimes, it hides little clues in how fast or slow things move. Reach out. Feel the faint warmth of this newborn star beside us. It's not hot like you'd expect. Out here, even blazing things feel calm, because they're so far away, because space is patient. The light from this star? It began traveling before you were born, before your grandparents were born, maybe even before humans figured out fire. And yet, here it is, just arriving. Just now brushing your hand. Time in space is a traveler, too. You and I, we're not frozen, even when it feels like it. We're moving, around the sun, around the galaxy, around something even larger we can't quite see. And all that movement? It bends the path of time. On Earth, you might set a clock and expect it to match someone else's. But out here, 2 astronauts floating apart will age differently. Just a tiny bit, sure, but still. Imagine spending 6 months on the International Space Station, watching the sun rise and fall 16 times a day. When you come home, time has nudged you. You're just the tiniest sliver younger than your twin down below. Isn't that wild? Let's float backward now, way back, past Mars, past the asteroid belt, each rock a frozen second, locked in orbit, and past Jupiter's swirling storms. Feel the size of it. That planet is so huge, its gravity even slows time more than Earth's does. If you lived there, not that it's a great place for a summer home, your clock would tick a little differently than someone sipping coffee on Earth. But we're going further, out to Saturn where the rings whisper in ice, past Uranus and Neptune, where blue gas giants sleep in the shadows. Time slows out here too, not because of gravity but because of speed. The slower you go, the less you notice time shifting, but start moving fast, really fast, and things begin to stretch again. Imagine a spaceship zooming at a good chunk of the speed of light. Inside, the crew reads books, plays cards, maybe tells stories like this one. To them, all is normal. But when they return to Earth, decades have passed, generations even. That's special relativity at work, but you don't need to memorize the name. Just remember the feeling. The sensation of time flowing differently, depending on where you are and how you move. Let's pause here. Just outside Pluto's ghostly orbit, feel how quiet it gets. The sun is just another bright star now, and the heat is barely a whisper. But even here, time moves. Slow, steady, cold. There's a comfort to it, isn't there? You and I, we're time travelers in the gentlest way, just by being here, just by noticing. Watching a comet sail by, dragging its icy tail like a scarf in the wind, we're witnessing ancient things unfold in slow motion. Now, lean in, look closely. See that pale dot in the distance? That's Voyager 1 still whispering back to Earth after all these years. It carries our hellos, our music, our hopes on a golden record, and even its messages take hours to reach us now, because time in space isn't just measured in seconds, it's measured in distance, in patience, in waiting. So next time someone asks, how does time pass in space? You'll know. It passes oddly, it passes slowly, it passes fast. It depends where you are, how heavy things are, how fast you're going, but most of all, it passes with wonder. Now, should we keep floating? Let's not rush. Out here, we have all the time we need, or at least all the time space is willing to lend us. So lean back, let your mind drift, and keep your eyes on that horizon that never ends. See how it curves slightly, like the edge of a dream you're just about to understand? We've just passed Voyager, and even though its tiny metal heart still beats, it's quiet out here. You and I are so far from Earth now that even radio waves, those fast, invisible travelers, take more than 22 hours to say hello. Imagine whispering to someone and waiting almost a full day just to hear them whisper back. That's time, stretching itself between stars. You might be wondering, does time ever stop? It doesn't, not completely. Even in the quietest corners of space, time keeps ticking. But it does something strange near the edge of black holes. Imagine you're watching a friend, let's call them Sam, slowly lower toward one of those dark, gravity-heavy wells. You're safe, watching from a distance, but to you, Sam seems to slow down. Every movement, every wave of the hand becomes syrupy. As Sam approaches the event horizon, that edge beyond which not even light escapes time, from your point of view, nearly freezes. But for Sam, inside their helmet, everything feels normal. That's one of the strangest truths of space. Your time isn't always my time, and yet both are real. Let's slide sideways now, toward the center of our Milky Way galaxy. It's a long ride, we've got about 27,000 light years to cover. But that's the beauty of imagination. It doesn't need a warp drive. You and I can drift effortlessly through the thickening clouds of stars. Feel the density increasing. Look at all those suns, some packed only a few light weeks apart. That might still sound like a huge distance, but compared to the lonely edges of the galaxy, this is a bustling city. And at the heart of this city, a supermassive black hole, 4 million times the mass of our sun. It sits quietly, surrounded by stars that whip around it in tight, fast loops. They're moving at thousands of kilometers per second. Time near them, it ticks slower than yours or mine. You and I, floating a little farther out, watch them blur like fireflies in a jar. But to those stars, to any astronaut foolish enough to fly, that close time would feel smooth, just slower. In fact, 1 second near the black hole's edge could match hours, days, or even years for us out here. You might notice your breath now, slow and steady. Let it match the rhythm of space, which is to say, no rhythm at all, just gentle, flowing silence. That's where truth hides best. Now let's gently swing outward, into intergalactic space. It's colder here, quieter still. The stars are thinner, like whispers on a winter morning, but the story of time continues. Do you see that distant galaxy? The one spinning in soft blues and purples, like a whirlpool of light. That light left it maybe 200 million years ago, back when dinosaurs were still stomping around Earth. So what you're seeing, that's history, a live replay. When we look into space, we always look into the past. And the farther we look, the further back in time we reach. Now, picture a deep field, thousands of galaxies, all tucked into one small patch of sky no bigger than your fingernail held at arm's length. That's what the Hubble telescope showed us. Some of those galaxies are over 13 billion years old, meaning the light you're seeing began its journey just after the universe was born. Time, in this way, is stitched into space itself, like folds in a blanket or waves on a pond. It isn't something separate, it's part of the same fabric. Feel that idea for a moment. Reach out and imagine the very fabric of space-time. It's not something you can touch, but it reacts to mass. It reacts to energy. A big object like a planet or a star bends the fabric. That bending tells other things how to move. And that bending, that's also how time gets distorted. The more massive the object, the deeper the dent. And the deeper the dent, the slower time flows within it. So here, as we float through empty space, time runs a little faster than it does on Earth, because there's less gravity holding it back. Now, picture Earth again. We're way out here, but let's look back. Earth is spinning, circling the sun, which is circling the galactic center. All that motion, it affects how time flows. Not just gravity, but speed. This is why GPS satellites, those little machines that help your phone tell you where the nearest coffee shop is, have to constantly correct their clocks. They're higher up, farther from Earth's pull, and they're moving fast. Without adjustments, they drift out of sync by several microseconds per day. And while that sounds tiny, it's enough to completely throw off location accuracy. You'd think you were standing in the middle of a lake when you're really on the sidewalk. So yes, even our technology has to understand how time passes in space. Let's ease our way into a nearby star system now. See that orange glow? That's a red dwarf, smaller and cooler than our sun. Planets swirl around it in tight orbits. Because the star is so small, its planets have to be close to stay warm. Some of them are tidally locked, meaning one side always faces the star, the other always faces darkness. So time on those planets? It's strange. One eternal day, one eternal night, a loop of heat and shadow. If you lived there, you'd mark time differently, not by sunrise and sunset, but by something else entirely, maybe the rhythms of wind, or how often your planet wobbles just slightly. Let's imagine you're on one of those planets. Step out from your shelter, feel the warmth of the sun side, hot and dry. Step into the night side, and frost forms instantly on your breath. What kind of clock would you build here? Now float back beside me. There's more to see. Look out past the galactic plane. There, do you see that faint smudge? That's the Andromeda galaxy. It's moving toward us. Slowly. In about 4 billion years, it'll merge with our own galaxy. The stars won't crash, there's too much space between them, but gravity will pull and stretch and twist everything. When galaxies collide, time gets turbulent. Stars speed up, some are flung out, others sink toward new centers of gravity. The flow of time in those regions shifts again. A vast, slow ballet, but with every twist, the clock ticks a little differently. You might notice, by now, that everything we touch out here seems to carry time in its bones. Even the coldest dust cloud, floating in deep silence, is on a timeline. The atoms within it are waiting to collapse, to heat up, to ignite, to become something more. Stars are born, they burn, they die. And even in death, they mark time, a white dwarf cooling over billions of years, a neutron star spinning its final pulses into the dark, a black hole slowly evaporating across unimaginable eons. Let's pause here again. Float still. Let space hum. Time doesn't tick, not like a clock. It flows. It stretches. It folds, bends, and sometimes hides. but it never stops, not even in the deepest cold. And you? You've been floating here for a while now, but back on Earth, maybe only 10 minutes have passed, or maybe more. It's hard to say. That's the magic of these journeys. Now, look out one more time. See that long, thin thread of galaxies, stretching like pearls across the blackness. That's part of the cosmic web, the structure of the universe itself. And yes, even that has its own timeline. Galaxies collide, fade, vanish. Dark energy, mysterious and gentle, pulls at the edges, making space itself expand. The farther something is, the faster it moves away from us. And that movement, it stretches the light, turns it red. This redshift is time too, a sign that space is growing, that even nothing moves. Take a deep breath with me. Slow, easy. Feel how the air moves into your chest, or at least how it would if we weren't out here in the quiet hush of vacuum. You don't need lungs in a dream like this, just your curiosity and a steady willingness to float. Out ahead, the stars are thinning again. We've left behind the warm traffic of galaxies and slipped into one of the great voids between. These are unimaginably vast regions where matter is sparse, light years of darkness between each lonely dot of light. You might think time would stop here, but it doesn't. If anything, it runs smooth and quick, unbothered by gravity or speed. There's almost nothing here to weigh it down. Reach out and feel that emptiness. It's not cold in the way your hands would feel on a winter day. It's a different kind of cold. The kind that's so ancient, so stretched thin by time, that it barely remembers warmth. The background temperature of space, even in its most distant corners, hovers just above absolute zero, about 2.7 degrees above to be exact. That tiny whisper of heat, that's the afterglow of the Big Bang. Let's sit with that for a moment. Over 13 billion years ago, the universe began as something hot and dense and bright, and then expanded outward, fast, furious, but not with noise, just with energy. And that energy cooled, and it stretched, and it thinned, until what remained was this background hum, a microwave murmur of creation itself. Time began then, too. Before that moment, there was no before, not just in terms of space, but in terms of time itself, because time and space are married. One can't exist without the other. They were born together, twins, spinning hand in hand ever since. Now, imagine being there, not in a spaceship, not in a body, but as a witness, a flicker of thought, watching everything blink into existence. What would time feel like then? Not slow, not fast, just brand new, like hearing music for the first time, like noticing your own heartbeat. We're not just drifting through time, we're swimming in it. Let's gently move again. Turn your gaze to that soft ripple ahead. That's a stellar nursery, a nebula where new stars are being born. Dust and gas swirl, pulled inward by gravity, pushed outward by light, in a dance that takes millions of years to complete. From afar, it's a colorful cloud. Up close, it's chaos. But beautiful chaos. Come closer. Feel the grains of dust slide between your fingers like cosmic sand. Each one may one day be part of a planet, a moon, or even part of someone's heartbeat. Now, let me tell you something wonderful. Stars are clocks. Each type of star lives for a different span. A massive blue star might blaze for only 10 million years, then explode, gone in a supernova flash. But a small red dwarf? It can live for trillions of years. In fact, the universe isn't even old enough yet for any of them to have died of natural causes. They're still out there, burning low and slow, patient keepers of cosmic time. So when we look at a star, we're seeing more than light. We're seeing a lifespan in motion, a ticking clock made of fusion and flame. And here's another fact. Your body is full of stardust. Literally. The carbon in your cells, the calcium in your bones, the iron in your blood, all forged inside long dead stars. When those stars exploded, they scattered their elements across space, and eventually, those pieces found each other again, in planets, in oceans, in you. So in a very real way, you've already traveled through time. You've been atoms in a star. You've been part of deep space. Now, you're listening to a story about time while being made of it. Let's push outward again. Up ahead. See that burst of light? That's a gamma ray burst, one of the brightest events in the universe. It happens when a massive star dies just right, or when two neutron stars collide, crushing their matter into something even denser. The burst lasts seconds, maybe minutes, but the light races across billions of years to reach us. That's how long it can take a moment to arrive. And here's something even stranger. Because the universe is expanding, the light we see from far away is also stretched. It's redshifted, shifted into longer wavelengths. But that means the further back we look, the more time seems to slow down. Events that lasted seconds may appear to us as minutes or longer, because the fabric between us and them has stretched. Imagine trying to watch a movie while the screen itself is being pulled apart. Now float with me into a globular cluster, a dense sphere of stars, all tightly packed together like fireflies in a jar. Here, time is pulled in odd directions. Gravity is stronger, so clocks inside the cluster tick a bit slower than those on the outside. You wouldn't notice it unless you had very sensitive instruments, but it's there, always there. That's the truth of time in space. It never flows the same way twice. Let's turn inward, toward ourselves for a moment. Time inside your own body isn't even uniform. Did you know that? Gravity on your feet is slightly stronger than gravity on your head, so time ticks just a fraction slower at your toes than at your ears. The difference is so tiny, it's nearly impossible to measure, but it's real. So, if even your own height contains different timelines, imagine what happens across galaxies. Now watch that planet ahead. It's orbiting a white dwarf, a small, dim remnant of a star. The planet's year is short. It zips around in just a few days. Time, for any creatures living there, if there are any, would feel different, not because of how they measure it, but because of how light and gravity shape it. And here's a beautiful idea. If a civilization lived on a planet with slow time, and they looked out at Earth, they might see us rushing, speeding through history. Blink, and we've gone from fire to fiber optics. Blink again, and we've left the planet entirely. To them, we'd be fast creatures, bursts of thought in the cosmos. But to someone watching Earth from the future, we're just beginning. Let's tilt now towards something vast, a galaxy cluster. Thousands of galaxies bound together by gravity, swimming in dark matter. The space between them hums with energy. And time flows differently inside the cluster's gravity well than in the emptier regions outside. Light curves around the edges. Images double and twist. You're not just seeing things, you're seeing time reshaped. That phenomenon? It's called gravitational lensing, and it lets us see galaxies that would otherwise be hidden. The cluster bends light around itself, like a lens or like time looking in a mirror. And here's something to imagine. One day, maybe far in the future, humans will travel fast enough to experience real-time shifts. Not just tiny ones like on the space station, but noticeable ones. A crew might leave Earth, travel near a black hole, or accelerate to near-light speed, and return to find the planet completely changed, their loved ones older, their cities transformed. It would feel like time travel, because in a way, it is. Let's slow again. Float with me. Let your mind settle into the stillness of it all. Because here's the quiet truth. Time in space is not a single thread. It's a web, a shimmering, bending, vibrating thing. It touches everything. It flows through stars and comets, through bones and thoughts, and it's still carrying the first heartbeat of the universe even now. Let's pick up right where we left off, just you and me, riding that ancient heartbeat. Now feel the drift. There's no rush, no destination, just the slow dance of light and time curving around your fingertips. You might start to notice something strange. It's not just stars and black holes and planets that shape time out here. It's everything, every bit of energy, every curve in the path. Even emptiness has a rhythm. We're gliding now through an interstellar dust lane, thick clouds of gas and particles stretched between stars like smoke caught in slow motion. And yet, even this smoke has age. Some parts of this cloud are older than Earth, older than our sun. They've been floating here since before our solar system existed, drifting, waiting. You can reach out and feel it. Cold, fine like flour, dotted with carbon, silicates, frozen water. These particles may one day swirl into a new solar system, another star, another planet. They may become a sky, or a sea, or the spark of a heartbeat in something new. Time flows differently here. Not faster or slower in a clock sense, but differently in the way it's perceived. Nothing hurries. Gravity is gentle. The days of stars are counted in millions and billions. The kind of time that makes you feel very, very small. But in that smallness, there's peace. Now we'll move again. Not far, just enough to drift near a binary star system. See them? Two suns, locked in a glowing embrace. One white, one a soft peach gold. They orbit each other in a slow, precise spiral, like partners in a dance. This system is a beautiful way to see time at work because their orbit marks it out. Every cycle a silent calendar. Now imagine living on a planet orbiting both those suns. The light would change throughout the day, not just rising and setting, but overlapping, twisting shadows, dual sunrises, glowing evenings. Time would be felt through light patterns, through warmth, shifting in unexpected ways. You wouldn't count hours like we do on Earth, you'd feel time through movement and brightness, through seasons measured by solar geometry, not just distance. And here's something real. Some binary stars are so close they distort each other. Gravity pulls one star into an egg shape, while the other siphons off its matter in a gentle cosmic leak. This mass transfer changes how both stars age. One burns faster, one swells with new fuel. Their relationship literally reshapes the flow of their time. Can you feel how rich this is? Let's keep following this idea. Right now, floating past the orbits of stars, we're inside what astronomers call a stellar stream. These are long, ribbon-like trails of stars, pulled from old galaxies or clusters that got too close to something bigger. Gravity unravels them, stretching the group into a flowing chain of stars that keeps orbiting long after the original structure is gone. In this stream, time is traced not in seconds or days, but in paths. Each star follows its own arc, a memory of where it came from. They look calm now, but this was once the chaos of cosmic tearing of things falling apart and reforming. Time, here, is a sculptor. It doesn't just pass, it molds. It stretches the cosmos into shapes you can't see from a single moment. You have to watch for ages. You have to trust the slow unfolding of things. And that's the heart of space-time. It doesn't care about what's fast for us. It moves with patience beyond anything on Earth. Now gently spin with me toward a quasar. That bright light ahead, it's not just a star, it's a beacon from a galaxy's heart, lit by a supermassive black hole devouring matter faster than it can digest. As the material spirals in, it heats up, spins faster, and emits blazing jets that reach across thousands of light years. You're not just seeing light, you're seeing time compressed into raw energy. From this distance, the quasar looks frozen, but if we waited, truly waited, we'd see it dim, flicker, wane. These things don't burn forever. Even the brightest moments in space eventually pass. And the time it takes to fade? Sometimes billions of years. Imagine watching something that bright, knowing it's already gone dim by the time you see it, that its light left when Earth was still an ocean full of single-celled wanderers. That's how deep time works. You never see the thing itself, only its past. Let's follow one of those jets now. We'll ride it outward, as if surfing a beam of light. Ahead of us, space curves ever so slightly, not because there's a planet or a star in the way, but because energy itself has weight. These streams of particles distort space as they travel. Time bends subtly, just enough. And now we find ourselves beside a rogue planet, a world drifting alone between stars. No sun, no orbit, just a cold ball of rock and maybe ice, wrapped in eternal night. You might think time would be meaningless here, but even here, time ticks. There might be geothermal heat below the surface, a warm core, cracks in the crust where chemistry happens, maybe even liquid water trapped in underground oceans. If there's life here, and that's still a big if, it would know time differently, through chemical change, through pressure and vibration, through the occasional flash of heat from the planet's shifting heart. You can almost hear it, like a heartbeat deep underground. Even without a sun, this planet still moves, through space, through time, orbiting the galactic center like everything else. Nothing stands still out here. And now, look there, a fast radio burst. Just a flicker, a pulse of radio waves that came from billions of light years away. We don't fully understand them yet. They last milliseconds, but the energy they release is enormous. Some theories say they come from magnetars, neutron stars, with magnetic fields trillions of times stronger than Earth's. In less than the time it takes to blink, a magnetar might release as much energy as our sun does in a century. And we feel that moment, that blink, long after it's passed. Because time is like that. A single instant can echo forever. Now we're crossing the plane of a spiral galaxy, its arms stretched out like ribbons of silk. Each arm contains young stars, gas clouds, dust lanes. The spiral shape isn't a fixed structure, it's a wave, moving through the galaxy like a ripple on a pond. Stars are born and die within it, like leaves on a branch that's always growing, always moving forward. The galaxy rotates, but not like a solid object. The outer parts move slower than the inner ones. So, over billions of years, the spiral pattern should unravel. But it doesn't. Something, maybe dark matter, holds it together. Something invisible keeps time's fingerprints from smearing the shape. We still don't know exactly how. That mystery is part of the wonder. And that's the truth. Space isn't finished. It's still unfolding, still changing, still being shaped by time, and shaping time in return. Even light isn't exempt. As it travels across expanding space, it stretches, its color shifts, its energy fades. A photon born in the heart of a star might take thousands of years just to reach the star's surface, then millions more to reach us. And yet, when it finally lands in a telescope, or an eye, or on your hand outstretched here beside me, it carries all that history, all that time. You've been touched by ancient light. Let's keep going. There's no rush, no ending, just motion, just moments, just this. The galaxy behind us spins slowly, its arms dragging light and time with them, but we don't look back. There's always something ahead. And time, well, it always moves forward, at least from where we're standing. The trick is, out here, forward depends entirely on where you are and how you're moving. Now imagine this. A spacecraft not ours is accelerating steadily, not to light speed, not quite, but close, maybe 99.9% the speed of light. Inside that ship, time slows. Not because the crew feels it, they don't. They eat, sleep, play cards, talk nonsense about who forgot to feed the space cat just like usual. But to an outside observer, they seem suspended, like a film running in slow motion. If they kept going that fast long enough, they could travel 100 years into Earth's future, while aging just a few months. It's not science fiction, it's relativity, proven, measured. Speed bends time. Let's swing downward now, toward a dense cluster of neutron stars. You probably feel it before you see it, the heavy sensation, the press of gravity that doesn't touch your skin but tugs somewhere deeper. These stars are the remnants of massive ones that died in supernova explosions. What's left is incredibly small and heavy, like cramming a mountain into a teaspoon. And here, around these spinning hearts, time contorts again. Their gravity slows it, their spin twists it. Some of these neutron stars, pulsars, emit beams of radio waves with clockwork precision, millisecond pulses, ticking perfectly, over and over. So perfectly, in fact, that we use them as cosmic clocks. You can reach toward one now, if you want, not too close. Just feel the rhythm, that steady thump of radiation. Tick, tick, tick. Each one is a heartbeat of time measured against the universe's backdrop. And between them, in the quiet voids, time flows more freely, less tugged, less slowed. Everything is relative, always. Now let's talk about cosmic inflation. It's not something we can see, not directly, but it happened almost certainly in the first fraction of a second after the universe began. Not just an explosion, but a sudden, unimaginable expansion. Space itself stretched faster than light could travel across it. It didn't break any rules because it wasn't things moving through space. It was space expanding itself. Time began to make sense during that inflation. Before that, we don't really know what time even was, if it existed at all. Some theories suggest that time itself could have been curled up, looped in on itself, or flat, or frozen. We have hints, equations, ideas, but no memories, nothing to hold in our hands. What we do have is the cosmic microwave background, the earliest light we can see. It comes from about 380, 0 years after the Big Bang, when the universe finally cooled enough for atoms to form. Before that, it was just a glowing fog, too hot for light to move freely. But then, suddenly clarity. That light still washes over everything. You're swimming in it now. Every part of the sky, every direction, carries its glow. If your eyes could see microwaves, the night would never be dark. Even silence has history. Let's float towards something subtler now. See that thin arc of starlight bent around nothing? That's gravitational lensing. We've seen it before, but here it's more delicate, a single distant galaxy, warped by the mass of something we can't even see. Maybe a black hole, maybe dark matter. The image bends, but the light is old, very old. And as we study it, we notice something strange, not just the bending but the delay. Some paths that light takes are longer than others. We see the same object more than once echoes of itself from different angles and different moments in time. Imagine looking at a person and seeing their smile from 1 second ago, their blink from 5 seconds ago, and their wave from 10, all layered together in the same view. That's what gravitational lensing does. It lets us see how time can split, can delay, can double. It's beautiful and deeply weird. Now look ahead again. We're approaching a stellar remnant, a white dwarf surrounded by a glowing planetary nebula. You'd expect a planet, maybe, but this isn't that. The name's misleading. What we're seeing is the final breath of a dying star, casting off its outer layers in waves of light and gas. That glowing shell is moving outward, expanding slowly, and in doing so, it tells us how long ago the star died. We measure the speed, the spread, the age. It's like reading a tree's rings, only in space. Even death has a timeline. And the white dwarf at the center? It'll cool, for billions of years, maybe longer, until it becomes a black dwarf, a theoretical object we've never observed, because the universe isn't old enough for one to exist yet. But one day, far in the future, there may be nothing left but black dwarfs and black holes, cold, slow, quiet. And even then, time will continue. Not for us, maybe, but for something. Now follow me toward the edge of a star-forming region. These nurseries of light and motion are wild places. Stars are born in them, pulled together from clouds of dust and hydrogen. Gravity collapses the gas. Pressure builds. Fusion ignites. A star is born. But it doesn't happen fast. From our point of view, it takes millions of years for that birth to complete. From the point of view of an atom caught in the middle, maybe it feels different. Maybe it feels like forever. Or maybe not at all. We don't know, because time doesn't feel. It just is. Still, we try to measure it, to understand it. We count time with stars, with light curves, with redshift, with the decay of radioactive atoms. These are our yardsticks in space. Did you know we've dated the oldest star in the Milky Way? HD 140,283. They call it the Methuselah star, about 14 billion years old. Which, if you're paying attention, is strange because the universe is only about 13.8 billion years old. How can a star be older than the universe? Well, it probably isn't. There's error in the measurements, but it's close, very close, which means this star formed just after the universe began, a time traveler by its very nature. We see its light now, but it's ancient. You and I, floating beside it, are looking into time's own mirror. And beyond it, there are stars we'll never see, galaxies whose light will never reach us, because the universe is expanding faster than the light can travel. That's not a theory, that's reality. There are places we can never touch, not because we lack the tools, but because time and space themselves have stretched the path beyond return. It's humbling, but also kind of comforting, because it means that there will always be mystery, always something just out of reach, and time with all its bending, slowing, stretching will keep on unfolding, whether we're here to see it or not. Feel the quiet, still around us like silk. There's no edge to space, no horizon where the stars fall off, just more of it infinite in all directions, or maybe not. Maybe it's curved inward, or looped like the surface of a balloon. We don't know, but we keep flying anyway, into what looks like forever. You might notice the black isn't really black. It's deep, layered, the way shadows are layered in fog. There are flecks of dust, strands of hydrogen, faraway flashes that barely register in your eyes. And all of them? Moving. changing, aging, even if they don't look like it. We're going to pass through a region of dark matter now. You won't see it, you won't feel it, but it's there. Holding the galaxy together like a hidden skeleton, dark matter doesn't glow. It doesn't emit light or reflect it. It slips through stars, planets, people completely invisible, and yet it has mass. And where there's mass, there's gravity. And where there's gravity, time bends. So yes, even the invisible things slow time. We're being tugged now, gently, not by a planet or a sun, but by a halo of something we can't touch, holding this galaxy in place. Without it, everything we see would unravel, fling itself outward in a spinning mess. But because of this quiet, unseen weight, the stars stay near each other, the spiral arms keep their shape. The galaxy continues to exist. That's dark matter's gift. Structure. We ride past stars that have been dead for billions of years, their light still echoing forward. We pass others that haven't even formed yet, just clouds, full of promise, slowly collapsing. If we paused here for long enough millions of years, we'd see a star bloom into being right in front of us. Light would flicker, gravity would tighten, dust would glow. But that's the thing. Time moves faster for the patient. Let's change directions. Upward now, relative to the galactic plane. Though really, up has no meaning out here. It's just a way of saying, a new place. Picture us arcing over the disk of stars, seeing it from above. It's so thin, like a coin floating in the dark. Most of the galaxy's light clings to that disk, but around it, above and below, is the halo. And in the halo, ancient stars. Some of the oldest in the universe live here, far from the noisy gas and dust of the star-forming regions. These stars are quiet, burnt-down embers, low on fuel, rich in age. They drift slowly, orbiting the center in long, elliptical paths. Some of them only complete a single full orbit every few 100 million years. If they had calendars, they'd be measured in entire civilizations. And just like with Earth, speed and gravity change how time flows here. So depending on how fast a star moves through the galaxy, its time might flow just a little differently than the ones near the core. Even stars experience time their own way. And now look ahead, a hypervelocity star. Yes, they exist. A star ejected from the galactic core, flung outward at incredible speeds, faster than the pull of the galaxy can hold. Some are thrown out by interactions with the black hole at the center. Others are pushed by violent supernova explosions. But once launched, they fly alone, untethered, tearing through space. Time for them is a blur. Because of their speed, their internal clocks tick slower compared to ours. Their entire journey, from galactic center to intergalactic space, might feel short from their perspective, just a long dash through darkness. But to us, watching from afar, it might span hundreds of millions of years. So we float near one now, watch it trail its life behind it like a scarf in the wind, a runaway, carrying its time like a secret. Let's fall inward again, toward that glowing band ahead, a galactic filament. This is one of the largest structures in the universe, a thread of galaxies, dozens or hundreds of millions of light years long, strung together like beads. Between the filaments, voids, immense, empty spaces where almost nothing lives. Time flows here, too. On the edges of clusters, light from galaxies warps. Their redshift tells us they're moving away faster and faster as the universe expands. And as they go, their time stretches. Each tick of their clocks, each flash of their light, comes to us slower and longer. They aren't slowing down, we're just farther away. Let's take a moment and hover inside one of those voids. It's not truly empty, nothing in space is, but it's quieter here than almost anywhere else. The galaxies are dimmer, thinner, scattered across the edges. In the center, just blackness. A lonely particle here, a rogue photon there. This is as close as we get to timelessness. But even here, in this calm, time is still moving, slowly. Even the absence of gravity, the stillness of near nothing, allows for the purest, fastest flow of time. Nothing is pulling it down, nothing is bending it. So here, clocks would tick their fastest. Not noticeably, but measurably. Strange, right? The emptier the space, the quicker the time. Now let's slide toward a distant radio galaxy. You can see it ahead, its lobes of radio-emitting gas stretching out from the central core. These are powered by a supermassive black hole shooting out jets of plasma across hundreds of thousands of light years. The beams are older than human language. They've been moving through intergalactic space longer than Earth has had trees. And still, they go. If you watch closely, you'll see the gas gently pulsing in expansion over centuries. Time plays out like a slow heartbeat in the galaxy's veins. And surrounding it all is the intergalactic medium-thin gas that lies between galaxies, barely there, but still enough to trace temperature, motion, time. Over billions of years, this gas will cool, collapse, and gather again, and when it does, it will birth stars. Time in space is never wasted. It always becomes something. Let's keep moving now, not to anything in particular, just into more. Because everywhere you look, something is happening in silence. A photon is traveling, a planet is cooling, a black hole is spinning, and all of it, every single bit, is shaped by the way time chooses to flow. We may never stop and measure it directly, but out here, we feel it. Reach forward for a moment. Let your fingers graze the starlight ahead. What you're touching, not that you really can, left its star maybe 10,000 years ago. That means if the star exploded 5,000 years ago, we'd still be seeing it today, shining as if nothing happened. Because in space, what you see is always the past. Every twinkle is a memory. And the farther we look, the farther back in time we're seeing. Now that's a fact about space. Light has a speed limit, about 300,000 kilometers per second. It's fast, sure, but not instant. So, when you look at the moon, you're seeing it as it was 1 1/3 seconds ago. The sun, 8 minutes in the past. Alpha Centauri, our closest star neighbor, over 4 years behind schedule. Let's glide further. Here's something fun. Time doesn't tick the same on the International Space Station as it does on Earth. Because astronauts are moving fast and orbiting in a weaker part of Earth's gravity, time for them passes just a tiny bit differently. Astronauts on the ISS age very slightly slower than people on the ground. You'll see it there, glowing dimly, spinning wildly. Some neutron stars, especially the ones called pulsars, spin hundreds of times per second. And they're tiny, barely 20 kilometers across, yet they contain more mass than the Sun, which means the gravity at their surface is absolutely crushing. 1 teaspoon of neutron star matter would weigh about 1 billion tons. Because of this insane gravity, time near a neutron star passes slower than anywhere near Earth. If we could hover right above its crust without getting squashed or vaporized, we'd experience time crawling. You could live for 5 minutes there, while an hour might pass for someone floating safely far away. You can feel the tug, can't you? The way space itself bends around such mass. This is called gravitational time dilation, and it happens all over space. Now let's move toward the edge of a black hole, the ultimate test of time. That ring of glowing light, that's the accretion disk, full of gas and dust, swirling at nearly the speed of light, heating up as it falls inward. If we hover just outside the event horizon, the point of no return, something strange happens. Time almost stops. If you stayed there, perfectly still, just above the event horizon, your clock would tick much slower than a clock back on Earth. You could spend a few minutes here, and when you return, if you ever could, decades or centuries might have passed elsewhere. This is no theory, we've seen it in action. The star Stu orbits the supermassive black hole at the center of the Milky Way, called Sagittarius A. Astronomers observed that as Stu gets close to the black hole, its light gets redshifted, meaning its clock and everything about it slows down from our point of view. That's real-time relativity, happening in the heart of our own galaxy. Now keep flying with me. You see that twin star system up ahead? 2 stars orbiting each other, locked in a dance. One's a white dwarf, the other, a sun-like star. As they spin, they emit gravitational waves, ripples in space-time itself. We've detected these waves here on Earth using instruments like LIGO. And the incredible part? They carry time information. Those ripples, tiny as they are, show us how time can stretch and wobble when huge masses accelerate or collide. Every merger, every burst, every black hole collision tells a story in space-time. And we've only just started listening. Now, look over to the right. That's a globular cluster, a dense ball of ancient stars, all clumped tightly together. Some of these stars are over 13 billion years old. That's almost as old as the universe itself. They've been orbiting each other since before Earth existed. Because they live so far from galaxies and in relatively weaker gravity, their clocks have ticked a little faster than stars buried deep in galactic cores. So in a strange way, the oldest stars may have experienced more time than the younger ones. Let's keep going. You see that odd pattern ahead? That's the cosmic microwave background. It's the oldest light we can see, the afterglow of the Big Bang itself. About 13.8 billion years old, this faint radiation fills all of space. And it's not just a wallpaper, it's a clock. By measuring the tiny fluctuations in that light, scientists can determine the age of the universe, the expansion rate, and even how time passed differently in the early cosmos. And here's something cool. In the early universe, time passed differently because the density and temperature were much higher. The first 3 minutes after the Big Bang were more eventful than entire centuries today. Matter formed, neutrons combined, light decoupled from matter, all in a blink. If you were alive back then, somehow your perception of time would be completely different. The universe was hotter, denser, and faster. Expansion was wild. Now, billions of years later, everything has cooled, spread out, and slowed down. Time has stretched, just like space has. And now, as the universe expands, galaxies farther from us move away faster and faster. Some are already moving away faster than the speed of light, not because they're breaking physics, but because space itself is expanding between us and them. So their light will never reach us. They're disappearing from our universe forever. That's not poetic. That's measurable. It means the further we look, the more time gets distorted. Eventually, galaxies will vanish from view not because they die, but because time itself stretches too far for their light to catch up. Time, in space, is stitched to distance. The farther something is, the further back in time we see it. The deeper the gravity, the slower time flows. The faster you move, the more your minutes stretch into hours for everyone else. All of this, all these truths happen silently. But we feel them, don't we? Feel the chill in the dark between stars. There's no wind here, no sound, just you, the stars, and the steady passing of time. Or rather, times, because in space, there's no single clock. Every object, every observer, every gravitational pocket runs its own little timeline. Let's visit one of my favorite spots, a gravitational lens. See that massive galaxy cluster ahead? Light from a much more distant galaxy is traveling toward us, but when it reaches the cluster, it bends around it, as if space itself is being pulled like taffy. This bending isn't just a neat trick, it's a clue about time. Gravitational lensing doesn't just change where we see something, it changes when we see it. The light takes longer to reach us, curling around heavy masses. That means one part of the image we receive could show the galaxy as it was 100 million years ago, while another part could show it just a few million years later. Same galaxy, same moment, split across time by gravity. You might even see multiple images of the same supernova, popping like fireworks in different places, but they're the same explosion, seen at different moments. Imagine watching a single star die, again and again, with years between flashes. Now let's drift toward a satellite orbiting Earth, one of the GPS satellites up in medium Earth orbit. Here's something grounded and wild. GPS wouldn't work if we didn't account for time dilation. Each of those satellites is experiencing two forms of time distortion. They move fast, so special relativity makes their clocks run slower. They're farther from Earth's center of gravity, so general relativity makes their clocks run faster. And guess what? The second effect wins, so their clocks tick faster than those on Earth by about 38 microseconds per day. Tiny? Sure, but if we didn't correct for that, your GPS location would be off by several kilometers each day. You'd be lost in your own neighborhood. So every time you get directions to the coffee shop or track a delivery van, you're using a technology that literally depends on Einstein's theories of time. Now, let's curve around a red giant star, see how it swells and flickers. This star is nearing the end of its life, and it's beginning to shed its outer layers. The process takes thousands of years, but from our perspective, depending on how close we get or how deep into its gravity we fall, the event might stretch or shrink. Here's a fact. The stronger the gravity, the slower the tick. Even the cores of massive planets like Jupiter experience time slightly differently from their cloud tops. The difference is fractions of a second per year, but it's still there. Let's float near the event horizon of a black hole again, a bit closer this time. This region here, just outside the edge, is where time begins to seriously misbehave. A clock here would tick slower and slower the closer it gets to the edge. From far away, someone watching you fall in would never see you cross the event horizon. You'd appear to freeze in time. But from your perspective, you'd fall in fast, and once you pass the event horizon, there's no turning back. All timelines lead inward. And here's the craziest part. If you could survive and observe the universe from inside a black hole, and I'm stretching imagination here, you might see the entire future of the universe unfold in front of you before you're crushed by the singularity. Now glide back with me into calmness. Let's pause in a quiet nebula, the birthplace of stars. Here, clouds of gas and dust are slowly collapsing, pulled together by gravity. Over millions of years, they'll form stars, planets, and maybe even life. But here's a slower truth. Time in a star-forming nebula flows slightly faster than in a dense galaxy center. Why? Less gravity. So if a being were born here and lived billions of years in this calm, low-gravity region, they'd experience slightly more time than someone deep in a galaxy's core. And across vast epochs, even those slight differences add up. Let's keep that in your mind. Gravity changes the pace of time. It's not just about movement, it's about location too. Now look behind us, we've traveled across light years, but time hasn't flowed the same for every spot we've passed. A galaxy colliding with another might compress its stars and gas so tightly that time slows inside it. A fast-spinning neutron star creates a whirling mess of magnetic fields and gravitational tugs that distort time all around it. Even the universe itself is accelerating thanks to something called dark energy, and that means the way time expands is changing. Billions of years ago, the universe expanded more slowly, but now, it's picking up speed. Time is stretching faster with every passing moment. Here's a fact that still blows my mind. Most of the universe's future will be dark and slow. Galaxies will drift apart. Stars will burn out. Black holes will evaporate over trillions of years. Eventually, the universe will enter what's called the heat death, a state where everything is spread out, cold, and uneventful. No more stars, no more light, just particles. And time, moving on silently. We're lucky to live in a bright, busy time, a time when galaxies still shine, stars still burn, and clocks still tick with meaning. And even luckier, we get to float through it together, watching time flow in all its strange directions. Feel the soft pulse beneath your fingertips now. Not a heartbeat, but the subtle rhythm of a pulsar spinning hundreds of times per second. Imagine the sheer precision. These stellar remnants spin with clockwork accuracy that rivals the best atomic clocks on Earth. Each flash of their beams is like a cosmic lighthouse, sending time markers across space. Picture yourself drifting next to one now. The light sweeps past you again and again, so steady you could set your watch by ITIF watches worked out here. Because these spinning stars don't just tell time, they are timekeepers. Scientists use them to track gravitational waves, test Einstein's theories, and even help navigate spacecraft across the solar system. Can you hear the faint hum of their rotation? It's silent to human ears, but imagine if space could sing, this would be a deep, constant beat. Now glide slowly away and notice the difference in how time passes near such a dense, fast-spinning object compared to a calm, empty patch of space. Far from the pulsar, in the quiet darkness between galaxies, time flows steadily and peacefully. But near our spinning star, time ticks slower, stretched by intense gravity and rapid motion. Here's a fact. The stronger the gravity and the faster the spin, the more time slows down. So astronauts near a pulsar would age slower than friends watching from afar. A day for them might be years for us. Let's float toward a cluster of galaxies now. A swirling city of stars so vast they're measured in millions of light years. These clusters are bound together by gravity, but not evenly. At their cores, gravity is stronger, and time flows just a little slower compared to their outer edges. Imagine standing on a planet deep inside one of those central galaxies. Your clock would tick a tiny bit more slowly than someone living near the edge of the cluster. That difference is minute, imperceptible in everyday life, but over billions of years it means you'd experience less time passing. Feel the weight of that. Time itself is shaped by where you are in the universe. Slide closer to a white dwarf star, an Earth-sized ember left behind after a star like our Sun has finished burning. They're incredibly dense. A spoonful of white dwarf material weighs tons. Near the surface of a white dwarf, gravity is strong enough to bend light and slow time, but less extreme than neutron stars or black holes. Here's a fascinating fact. White dwarfs can help scientists measure the age of our galaxy because their cooling rate acts like a cosmic clock, ticking steadily as they fade over billions of years. Imagine reaching out and feeling the cool surface of one, glowing softly in the dark. The light you see left the star thousands of years ago, a delayed message from a dying sun. Drift now to the edge of a cosmic void, a vast emptiness stretching millions of light years across, nearly devoid of galaxies. Here, gravity is almost non-existent, and time flows almost at its fastest pace possible. If you could survive here, you would age faster relative to friends in denser parts of the universe. Time, it seems, loves company. It slows where matter crowds and races where space is empty. Breathe in the emptiness. No stars, no hum, just the quiet rush of time speeding through the void. And yet, even here, time is tied to space. The universe expands, carrying galaxies apart, stretching not just distance but also the fabric of time. Look up at the distant galaxies speeding away from us, some faster than light because space itself is growing. Their light will never reach us again, slipping beyond our cosmic horizon. Here's a profound fact. This expansion means that the observable universe, the part we can see, is only a fraction of what actually exists. Beyond this horizon, time and space continue, but we're forever cut off. Picture that our cosmic neighborhood is a glowing bubble in a vast, dark ocean of unreachable time and space. Now turn your attention to the cosmic microwave background, the faint glow left from the Big Bang. Feel its ancient heat washing over you, the echo of creation from nearly 14 billion years ago. This light has been traveling through space ever since, cooling, stretching, and carrying a record of the universe's infancy. Its subtle ripples reveal how matter clumped together to form galaxies, how time's early pace was different, faster, denser, more chaotic. Imagine riding a wave of this radiation, floating through time's dawn, feeling how the universe's clock began ticking, setting the rhythm for everything to come. Let's slow down here, in this primordial glow, and consider how time stretches across the universe. Every moment you've lived, every second past, is a tiny blip in this vast cosmic timeline. Yet the universe itself is a time machine, showing us snapshots from billions of years ago simply by looking farther and farther into space. Feel the wonder in that time is not just passing, it's layered, scattered across distance, warped by gravity, shaped by speed. And so we drift, companions on a journey through the flowing, bending river of cosmic time. Imagine you and I now drifting alongside a fast-moving spacecraft, not just any spacecraft, but one traveling at a significant fraction of the speed of light. Picture its sleek hull cutting through the blackness, stars streaking past as if we're inside a cosmic river rushing onward. Here's the mind-bending fact. When you move faster, your personal clock slows down relative to someone standing still. This isn't science fiction, it's time dilation in action, predicted by Einstein and confirmed in countless experiments. If our ship sped up to half the speed of light, your hour aboard would tick slower than my hour back home. After a few days at that speed, when you return, more time would have passed on Earth than for you. It's like stepping off an escalator that moves faster than everyone else's. You might feel only a minute, but decades could have passed outside. Think about the famous twins' paradoxone twin ventures into space at near light speed while the other stays on Earth. When the spacefaring twin returns, they've aged less. It's not just a story, it's a real effect of how time stretches and compresses with speed. Feel the sensation of moving through time at a different rate, your body untouched, but your moments flowing distinct from the rest of the universe. Now, let's slow down and hover near the surface of a massive star cluster packed with millions of stars in a tight space. The gravity here is intense, not enough to trap light like a black hole, but strong enough to warp time just a little. Scientists studying star clusters can measure this tiny warping by watching how light shifts and pulses. It's subtle, but over thousands of years, that slow tick means the stars inside age more slowly compared to those far away. Picture those stars living out their billions of years slightly out of sync with their galactic cousins. Time's subtle dance has many steps, and here's a new one. Drift now toward a binary star system, two stars locked in a close orbit, spinning around each other in a graceful, endless waltz. Because they're moving fast and tugging at each other's gravity, the flow of time near each star is different from the flow farther away. Imagine an observer standing on a planet orbiting one of these stars. Their clock would run differently than someone orbiting the other star, just because of their motion and position in the system. Here's a fact. Astronomers have used such systems to test general relativity by watching how time and gravity shape the light we see. The precision is incredible. Even small deviations help us refine our understanding of how the universe works. Let your mind wander to the thought of two clocks ticking out of sync, yet perfectly in step with their stars' movements and elegant cosmic rhythm. Let's drift outward again, this time toward the cosmic web, the vast network of filaments connecting galaxies across the universe. This web is mostly empty space, but it holds most of the universe's matter. Time flows differently along these filaments, where gravity pulls galaxies together, than in the huge empty voids in between. Imagine time as a river flowing faster through the emptier parts and slower where matter clumps. Feel how space itself is alive with this uneven tempo, a symphony of fast and slow notes played across billions of light years. Here's a striking fact. Light from the farthest reaches of this cosmic web takes billions of years to reach us, showing us not just distant places, but distant times moments when the universe was young and strange. Now, picture the aftermath of a supernova explosion, a star's final brilliant death throes. The blast sends shockwaves through space, stirring gas and dust, lighting up the sky for months or years. But time here plays a trick. The light from the explosion reaches us after the star has already been gone for thousands or millions of years. If you were standing near that star's remains, time might have flowed differently due to gravity, but the explosion's light races outward at a constant speed. You're catching a message, delayed by cosmic distance, a postcard from the past, arriving just now. Feel the thrill of receiving such messages, each one a timestamp from the universe's history book. Slide gently now toward a black hole's accretion disk, the swirling ring of gas and dust spiraling inward before vanishing past the event horizon. The matter here moves incredibly fast, heated to millions of degrees, glowing brightly in X-rays. Time near the disk slows dramatically compared to the outside universe. Imagine watching a particle falling inward. To a distant observer, its descent seems to take forever, stretched out by gravity's pull. But for the particle itself, the fall is swift and fatal. This duality of time, the outside perspective versus the falling experience, is one of the most fascinating puzzles of space. And it all boils down to the way gravity and speed reshape time's flow. As we float here, bathed in the ghostly X-ray glow, imagine what it means to live where seconds could stretch into years or blink by in moments depending on your point of view. Picture yourself drifting gently near a neutron star. These stellar remnants are the densest objects in the universe after black holes, packing more mass than our sun into a sphere barely 20 kilometers across. The gravity here is so extreme it warps time noticeably. If you held a clock close to this neutron star's surface, its ticks would slow compared to one far away. Here's a mind-bender. Neutron stars can spin hundreds of times per second. The faster they spin, the stronger their gravitational field distorts space and time around them. Imagine that spinning so fast that not only does time slow for you, but the star itself warps the very flow of seconds and minutes. Astronomers observe pulsar neutron stars emitting beams of radiation as some of the most precise clocks known. These beams sweep past Earth regularly, like a cosmic metronome. The timing is so exact that it helps detect ripples in space-time called gravitational wavestony shifts, caused by massive objects, like merging black holes billions of light-years away. Feel the quiet power of this star's ticking, keeping time that echoes across the cosmos. Now imagine yourself in a spacecraft orbiting close to a supermassive black hole at the center of a distant galaxy. These giants weigh millions to billions of times the sun's mass. Near their event horizon, time slows so dramatically that an hour there could equal years or centuries for someone watching from afar. Let's float just outside that boundary, where gravity stretches moments like warm taffy. If you looked out into space, distant galaxies might seem to rush past as your own time crawls. You might watch entire civilizations rise and fall in what feels like moments. Here's an astonishing fact. This extreme time dilation means that if you could escape before crossing the event horizon, you'd return to a universe aged far beyond your own lifespan. Feel the paradox of moving through a place where seconds expand and contract unpredictably, where the future and past blur. Glide away now toward the cosmic microwave background radiation, the oldest light in the universe. This glow bathes us in a whisper from nearly 14 billion years ago, just 380, 0 years after the Big Bang. That light has been traveling ever since, cooling and stretching as the universe expands. In a way, it's a ticking clock for cosmic time, showing how the universe has changed. Imagine drifting on this ancient wave, feeling time's immense depth like holding the universe's birth certificate in your hands. Now, let's travel to the outskirts of a galaxy cluster, where dark matter quietly governs the motions of stars and gas. Dark matter doesn't emit light or heat, but its gravity shapes the flow of time in subtle ways. Astronomers know it exists because galaxies spin faster than visible matter alone can explain, and gravitational lensing reveals its unseen pull. In areas rich with dark matter, time ticks ever so slightly slower than in empty space. The invisible mass bends not just light but also the fabric of space-time itself. Imagine feeling the invisible presence of this dark matter as you drift, sensing how it gently slows time around massive cosmic structures. Now let's peek at the role of cosmic expansion on time. The universe isn't static. It's stretching out in every direction. This expansion affects how time passes between galaxies. At great distances, galaxies recede so fast that their light shifts into longer, redder wavelengths, a phenomenon called redshift. Because light takes time to travel, we see distant galaxies as they were billions of years ago. The more distant the galaxy, the further back in time we look. Here's a beautiful fact. When we observe galaxies with very high redshift, we're looking at the universe's infancy, a time when stars and galaxies were just forming. Feel yourself stepping back through time, carried on light's wings from billions of years ago to this very moment. Slide over to a fast-moving spacecraft again, but this time imagine it's traveling close to the speed of light on a long journey. As it speeds up, time dilation becomes dramatic. For the travelers aboard, only months might pass, but back on Earth, decades or even centuries could flow by. This is why interstellar travel faces such deep challenges. Time becomes a strange companion, bending the experience of life and aging in unexpected ways. Imagine leaving your home behind, only to return to a future far beyond your own time. Now, picture the universe's ultimate future. Billions and trillions of years from now, stars will burn out, galaxies drift apart, and black holes slowly evaporate through a process called Hawking radiation. At that time, the universe will be cold and dark, with time ticking in near silence. Feel the calm, endless passage of time stretching into infinity, carrying the universe toward what scientists call heat death, a state where energy is spread evenly and no more work can be done. Yet, even in this quiet end, time flows on. Imagine yourself now drifting near a swirling galactic Korea place bustling with stars, gas, and dust, all spinning around a supermassive black hole. The intense gravity here bends light into arcs and warps time noticeably. You might notice stars near the core seem to move slower from a distant view. That's time dilation playing its subtle game, where gravity stretches moments. Here's something to hold on to. The black hole at the core's heart shapes not just space but also the flow of time, slowing it relative to regions farther out. If you could live near that core, your days would stretch longer compared to friends in calmer galaxy arms. Feel the energy pulsing here, a cosmic city alive with millions of years packed into each glance. Now drift outward toward a nebula, vast cloud of gas and dust where stars are born. Imagine the gentle glow of glowing hydrogen and helium, lit by newborn stars. Time here feels peaceful, yet this nursery is where the cosmic clock resets. New stars mark the start of fresh timelines, their nuclear fires beginning the steady pulse of their own time cycles. Astronomers measure ages of nebulae by the light emitted and the speed of expanding gases, revealing stories that span tens of thousands of years. Imagine reaching out and feeling the faint warmth of this newborn star beside us. Its light still fresh, its time just beginning. Float slowly through this birthplace, sensing the quiet patience of time as it cradles creation. Now turn your gaze toward cosmic background neutrino-elusive particles that have traveled since just 1 second after the Big Bang. Though invisible, they carry ancient information about the universe's earliest seconds, passing through space, through matter, through us, almost without a trace. Their journey tells us that time itself began not just with light, but with these fundamental particles racing outward from the dawn of existence. Imagine sensing this silent flood of history flowing past, a whisper of the universe's birth carried on particles smaller than atoms. Shift now to the realm of gravitational waves ripples in space-time, caused by massive cosmic events like merging black holes or neutron stars. First detected just a few years ago, these waves travel at light speed, stretching and squeezing space and time as they pass. Imagine feeling a gentle ripple wash over you, subtle but powerful, a cosmic heartbeat that tells us time is not just a line, but a fabric that can ripple and dance. Scientists use these waves to measure distances and test how time bends around the most extreme objects. It's as if the universe itself is sending us a message in pulses, showing time's dynamic nature. Glide gently toward a distant quasar, a bright beacon powered by a supermassive black hole feasting on gas. Quasars shine across billions of light-years, visible from Earth as ancient lighthouses. Because their light took so long to arrive, we see quasars as they were billions of years ago, offering windows into early cosmic time. Feel the glow of that light on your skin, a reminder that looking far out is looking back in time. Each photon tells a story from the universe's youth, traveling endlessly through the darkness. Let's drift now near a white dwarf binary system, where 2 dense stars orbit each other closely. Their gravitational dance emits subtle waves of energy and warps time around them. Astronomers measure their orbital periods to test time dilation effects and the intricate interplay of gravity and motion. Imagine being caught in this cosmic ballet, where time bends and flexes with every rotation. The precision of their timing helps unlock secrets of stellar evolution and the fate of our own sun billions of years in the future. Now, picture the slow passage of time inside a massive galaxy cluster's core compared to its outskirts. Time ticks slower in the dense, gravitationally strong center, meaning billions of years there might correspond to slightly more outside. Though imperceptible daily, over cosmic epochs, this difference shapes how stars age and galaxies evolve. Imagine witnessing galaxies at the center growing old slower, their light carrying subtle hints of time's warp. Feel the universe's heartbeat here, steady but varied. Slide away from matter-rich regions into vast cosmic void-empty expanses spanning millions of light years. Here, with almost no gravity to slow time, moments flow faster compared to crowded clusters. Imagine yourself in this emptiness, aging slightly quicker, time racing in the void's quiet vastness. This uneven flow of time across the cosmos reveals a universe alive with variety and wonder. Now, let's consider how cosmic inflation shaped time's earliest moments. Just after the Big Bang, space expanded faster than light, stretching the universe in a fraction of a second. This rapid growth set the stage for time's steady march ever since. Imagine inflation as the universe's first deep breath, expanding time and space to create everything we see. Scientists study this era through patterns in the cosmic microwave background, revealing how time's flow settled into the rhythm we experience now. Imagine the vastness born from that breath, a universe expanding and aging ever onward. Picture yourself now floating in the quiet vastness between galaxies, the intergalactic medium a thin, almost invisible mist of particles stretching across millions of light years. It's a place of almost perfect emptiness, where matter is so sparse that you might think time flows uninterrupted, a steady, silent river. But here's a fascinating fact. Time in these empty spaces is actually flowing just a little faster than it does near massive objects, because gravity's pull is weakest here. Without the heavy weight of stars, planets, or dark matter to slow it down, moments stretch out, and seconds slip by with gentle ease. Feel the silence around you, a peaceful tempo where light itself travels vast distances, carrying ancient stories from one end of the universe to the other. Now, Imagine that we're not just drifting, but also listening to the subtle echoes of the Big Bang, vibrations in the fabric of space-time itself, known as primordial gravitational waves. These are faint ripples left over from the universe's earliest moments nearly 14 billion years ago. Close your eyes and feel those waves, gentle and slow, like the aftershocks of a cosmic heartbeat that still pulses faintly through all of time and space. Scientists hunt for these whispers using powerful detectors buried deep underground or floating in space, hoping to unlock secrets about how time and space were born. Let's shift now to a remarkable idea: time inside a black hole's event horizon place, where the laws we know begin to unravel. If you were to cross this invisible boundary, time as you understand it would twist and warp in ways nearly impossible to imagine. From the outside, it looks like you freeze in place forever. But inside, time and space swap roles, and the future pulls you inward irresistibly. Feel the strange sensation of time losing its familiar flow, becoming a path you can't turn away from, rushing you toward the black hole's core. Physicists call this region a mystery, a place where quantum mechanics and gravity clash, and the true nature of time might be very different from what we know. Now, picture a space traveler orbiting a rotating black hole, or a Kerr black hole. Unlike a simple black hole, this one spins, dragging space and time with a phenomenon called frame dragging. Imagine standing near such a black hole, feeling the twisting of time itself, like a whirlpool in a river pulling your moments around in circles. If you sent a message outward, it would be delayed, stretched, and distorted by this spin, while for you, time might feel normal but strangely warped compared to distant observers. Scientists have theorized that near such objects, strange effects could even allow closed time-like curves, paths in space-time that loop back on themselves, a kind of cosmic time loop. Feel the dizzying possibility of time folding back, of moments connecting not just forward but backward, challenging everything we think about cause and effect. Let's gently float away from black holes and consider the effect of cosmic acceleration, the universe's expansion speeding up due to mysterious dark energy. This acceleration means that distant galaxies are moving away from us faster and faster, stretching not only space but also the intervals between events. As a result, some galaxies will eventually recede beyond our ability to see or communicate with them. Imagine standing on Earth, looking out into space, and realizing that over trillions of years, entire regions of the universe will slip away beyond our horizon, unreachable and frozen in time from our perspective. Feel the bittersweet flow of time carrying us forward, while pulling parts of the cosmos silently out of reach. Now, picture a hypothetical traveler moving near the speed of light, equipped with a clock and a radio. As they accelerate, their clock slows compared to Earth's, but their radio signals sent back home will stretch out, becoming weaker and slower to arrive. This is more than theory. Satellites in Earth orbit already experience tiny but measurable differences in time flow, and engineers must adjust for these in GPS systems. Feel the subtle weaving of time, technology, and motion, where time's flow is a practical matter as much as a cosmic mystery. Shift now to the scale of the multiversian idea that our universe might be just one of many, each with its own flow and fabric of time. Though purely speculative, some theories propose that time itself could vary wildly between universes. Imagine yourself as a cosmic traveler, drifting not just through space and time, but between realms where time's rules bend, stretch, or even rewind. Feel the thrill of the unknown, the vastness of possibility where time may be something new and strange, waiting to be discovered. Finally, picture yourself floating through the quiet hum of quantum fluctuations, random changes in energy and space-time at the smallest scales. These fluctuations blur the boundary between past and future, hinting that at the universe's heart, time might be less a smooth river and more a bubbling brook of possibility. Scientists continue to probe this realm, searching for clues about how time emerges from the quantum world into the flow we know. Feel the sparkling uncertainty, the flicker of time's birth at the tiniest scales, beneath the calm vastness of stars and galaxies. Picture yourself drifting in the vast darkness beyond the known universe, where even time as we understand it begins to fade. If time is the river that carries moments from past to future, then after time might be what lies beyond that river's flow if such a place exists at all. Some scientists imagine a future where the universe reaches a state called heat death, where all stars have burned out, black holes evaporated, and energy evenly spread so thin that nothing more can happen. In that calm, frozen silence, time might lose its meaning because change the heartbeat of time ceases. Imagine standing in a silent void, so still that seconds no longer pass in any meaningful way. Without change, without events to mark before and after, the concept of time might simply dissolve. But what could come after such a timeless state? Some theories suggest the universe might restart maybe through a big bounce, where after collapsing or fading away, it re-expands again, creating a new flow of time and space. Imagine a cosmic phoenix rising, reborn from timeless ashes, where a new beginning folds over the old. Other ideas propose that after time might mean stepping outside our familiar dimensions altogether. In advanced physics, there are hints that time could be an emergent property, arising from deeper, timeless realms. Picture that deeper layer as a calm, infinite ocean beneath the ripples of moments, a place where past, present, and future blend into a single, eternal now. If we could somehow glimpse beyond time, we might find a vast stillness, or maybe a new kind of flow beyond anything we've known. From a more philosophical view, some say time itself is a human experience, and what lies beyond time is simply the eternal, unchanging, infinite, and beyond words. Imagine resting there, where before and after don't exist, only endless being. Yet, for all our pondering, the idea of what happens after time remains a horizon just beyond our reach, inviting us to wonder and dream. Feel the quiet mystery in your chest, the pull of curiosity toward the infinite unknown. And though we can't say for sure what lies after time, exploring these questions brings us closer to the heart of existence itself. Imagine drifting now in a space so old and quiet that even the faintest flicker of a star feels like a bold defiance against the vast stillness. This is the far future of our cosmos, where time itself seems to slow toward a gentle stop, not because clocks break, but because events that mark time become impossibly rare. In such a universe, the very idea of after time feels less like a moment and more like a landscape, place where the familiar markers of past, present, and future begin to blur into one another. Picture the last photon, the very last particle of light, wandering through endless darkness. Without new interactions or changes, time's arrow the direction in which moments flow loses its pull. Some cosmologists call this state the heat death, but in that wordless silence, could there be something else? Something beyond the ticking of clocks and the turning of galaxies? Now, reach out with your mind and imagine a cosmic cycle, where time isn't a line but a circle, or perhaps a spiral. In these models, what looks like an ending might be the seed of a new beginning. This is the idea behind a cyclic universe, where after expanding and cooling, the cosmos might contract again, folding space and time back on themselves to start fresh. Imagine feeling the slow reversal of moments, where time might gently rewind or fold like a soft fabric, weaving new stories from the threads of old ones. Or maybe time flows differently in other regions, or other universes, entirely places where what we call after time is just a new kind of time altogether. Now, think about the strange quantum world, where time may not exist in the way we experience it. At the tiniest scales, time could be fuzzy, ill-defined, or even emerge from more fundamental, timeless laws. Scientists speak of quantum gravity theories that try to unite the deep rules of the very small with the vast cosmos, and in these ideas, time might be a secondary effect, something that appears only when many particles interact. Imagine diving beneath the waves of reality to find a calm sea without ripples, a place where past and future are one. Could the universe itself be a timeless whole, and our experience of flowing time just a slice of a greater timeless truth? Let's also ponder the role of consciousness in time. Some thinkers propose that without a mind to notice change, time might have no meaning at all. Imagine that time's flow depends not just on physics, but on perception, the dance between observer and observed. Feel how your presence here, in this moment, is part of that dance, weaving time's fabric into something alive and real. If we imagine after time as a state beyond all observation and change, it might be a place of perfect stillness, a vast potential for new realities yet to emerge. Now, turning back to space, consider the role of entropy, the universe's natural tendency toward disorder. Entropy gives time its arrow, pushing everything forward from ordered pasts to more disordered futures. When entropy reaches its peak, when everything is spread evenly and no more work can be done, time's arrow may flatten. Imagine entropy as the universe's gentle guide, carrying moments forward but eventually leading to quiet equilibrium. In that calm, could, after time, be the universe resting in a timeless balance? There's also the fascinating possibility of time loops, or closed time-like curves in some exotic regions of space, where time might curve back on itself. Imagine standing in such a loop, where moments repeat endlessly, or where cause and effect dance in circles. In these strange realms, after time might be just a turn away, a moment that folds back into itself like a Mobius strip. Though these ideas remain theoretical, they show how flexible and surprising time can be. As we drift here, surrounded by stars long gone and galaxies still forming, feel the vastness not just of space, but of time's mysterious nature. No matter how far we travel or how deeply we think, time invites us to wonder, to explore, and to imagine what might lie beyond its flow. Feel yourself gently floating now near a vast cluster of ancient stars, each one a glowing ember from a time billions of years before the dawn of Earth. As you look around, notice how these stars, though distant, are snapshots of different times. Their light takes millions or even billions of years to reach us, meaning when we see them, we're seeing into their past. Picture this cosmic time travel not with machines, but simply by looking at the sky. Each twinkle is a message from a different moment, sent across the universe's vast expanse. Now, consider the idea that time itself is not uniform everywhere. In regions where gravity is stronger, like near massive stars or black holes, time slows down relative to areas of weaker gravity. This phenomenon, known as gravitational time dilation, means that two clocks in different places might tick at different speeds. Reach out in your mind and feel the invisible tug of gravity, bending not just space but time, stretching and compressing moments like a cosmic rubber band. Imagine an astronaut orbiting a neutron star, a superdense remnant of a massive star's collapse. The gravity there is so intense that time for the astronaut might pass far more slowly compared to someone back on Earth. In this way, time becomes personal, flexible, and deeply connected to where you are in the universe. Shift your attention now to the realm of special relativity, where moving close to the speed of light affects how time flows. If you and I were traveling side by side at nearly the speed of light, your watch might tick normally to you, but mine, back on Earth, would seem to race ahead. When you return, less time will have passed for you than for those who stayed behind. This is called time dilation due to velocity. Imagine zipping through space at unfathomable speeds, experiencing time like a slow-motion movie, while the rest of the universe ages much faster. This isn't science fiction, but a reality proven by experiments with particles and satellites. Even the GPS satellites orbiting Earth must account for these effects to keep their time precise. Feel the astonishing flexibility of time itself, bending to the rhythms of speed and gravity. Now, picture yourself inside a giant cosmic clockwork, where the interplay of energy, matter, and space-time creates the steady march of time we experience. Yet, deep down, physics suggests time might not be fundamental. Some theories propose that time emerges from more basic elements, like the relationships between quantum events. Imagine time as a shadow cast by the complex dance of tiny particles, where cause and effect arise from entanglements and probabilities. This view challenges our everyday sense of a flowing river of time and invites us to see moments as interconnected points in a vast web. Feel the intricate weaving of moments and possibilities beneath the surface of what seems continuous and smooth. Let's also touch on the idea of the arrow of time. Why does time move forward, and why can't we remember the future? Entropy or disorder is key. As the universe ages, entropy increases, pushing time's flow forward. Imagine entropy as a cosmic storyteller, writing history one event at a time, never erasing what has been. Yet, at the smallest scales, the laws of physics don't prefer a direction. They work the same forward or backward, suggesting time's arrow arises from the large-scale behavior of matter. Reach out and feel the tension between the microscopic world's symmetry and the macroscopic world's irreversible flow. Finally, consider how life itself is a measure of time. Our memories, growth, and aging mark time's passage in ways even physics can't fully explain. Imagine yourself growing, learning, and changing, a living timeline embodying the universe's story. Our experience of time is rich and textured, woven from cosmic laws and personal moments. Imagine we're standing on the edge of time itself, peering beyond the last tick of the cosmic clock. What could lie beyond? Some theories suggest that after time as we know it ends, the universe might enter a new phase entirely different from anything we experience now. One idea is the concept of eternal recurrence, where the universe endlessly cycles through phases of birth, death, and rebirth. After the universe reaches a state of maximum entropy where all energy is evenly spread and no useful work can be done, it might collapse back, starting the cosmic clock again. Picture this cosmic loop, where after time is really just a fresh start, a new dance of stars and galaxies beginning once more. Other theories propose that time might not truly have an end at all, but could continue infinitely, bending and twisting in ways we don't yet understand. Feel the possibility that after time is less an end and more a transformation time evolving into a new dimension or merging with something beyond our perception. There's also the mind-bending idea from some quantum gravity theories that time is emergent, meaning it arises from more fundamental timeless laws. If so, after time could mean returning to a deeper reality where time simply doesn't exist. Imagine stepping out of the flow of moments into a timeless realm where all events coexist in a vast, unchanging present. This might be the true after, not a future moment, but a place beyond past and future, where existence itself is an eternal now. Another fascinating possibility involves multiverse theories, where our universe is just one bubble in a vast cosmic foam of many universes. After time ends here, maybe other universes with their own rules of time and space continue, or new universes spring into existence with different timelines. Imagine drifting among countless cosmic bubbles, each with its own story and flow of time, an endless ocean of creation beyond our own. Philosophically, some thinkers suggest that time's end could be akin to the universe reaching a state of perfect equilibrium, a cosmic stillness where nothing changes. In that quiet, after time, might be a kind of ultimate peace or rest, no more past, no more future, only an infinite present. Feel the profound silence that such a state would bring, like the deep calm at the bottom of the ocean after the last wave has passed. Yet, as we explore these theories, remember that after time remains a horizon, something just beyond our current understanding, inviting us to wonder rather than to know. It's a mystery that fuels both science and philosophy, reminding us how vast and strange the universe truly is. So, as we float here, suspended between moments and infinity, keep this sense of curiosity alive. The end of time might be a doorway, not a walla passage to wonders we have yet to imagine. Feel yourself drifting gently in the quiet depths of space, surrounded by swirling clouds of gas and dust, the birthplace of stars and planets. Here, time is more than just a measurement. It's a storyteller, recording every burst of light and every slow drift of matter. Time, you see, is woven into the very fabric of the cosmos. It's the rhythm that lets galaxies form, stars ignite, and life emerge. Imagine watching a newborn star flicker to life. What took millions of years for its light to travel to us is a single glowing moment in this star's time. This shows how time is relative. Different places in the universe have their own clocks, ticking at their own pace. Now, think about cosmic expansion, the universe itself, stretching like a balloon being gently inflated. Because space is growing, distant galaxies move away from us, and their light shifts toward redder colors, a phenomenon called redshift. Imagine that with every passing moment, space between galaxies grows, and with it, the flow of time across the cosmos stretches too. This expanding universe means that what we call now isn't the same everywhere. Time's flow depends on where you are and how the universe itself changes. Shift your focus to the small, quiet moments in space where particles dance and collide, where the tiny building blocks of matter pop in and out of existence. In these quantum realms, Time behaves oddly. It's fuzzy, uncertain, and sometimes it's not even clear if before and after really apply. Imagine time here as a misty fog rather than a sharp line, with events blending softly into one another. Scientists say this could be why the universe feels smooth and continuous at large scales, even though at the smallest scales, time is patchy and uncertain. Reach out and feel this delicate, shimmering layer beneath reality, where time's neat order melts into possibilities. And here's something to ponder: our own minds experience time uniquely. Memory threads past moments into stories, while anticipation pulls future possibilities close. Time inside us is alive, wrapped in feelings and senses. Picture how a single second can stretch out during a moment of wonder or shrink during a rush of activity. This personal time dances to rhythms different from those of clocks and planets. And yet, our minds are also connected to cosmic time, the rotation of Earth giving us day and night, the orbit around the sun marking seasons, the slow aging of stars tracing cosmic history. Feel how your own heartbeat is part of this grand temporal symphony. Finally, consider how time affects change itself. Without time, nothing could grow, move, or transform. It's the backdrop for every change: the paint drying, the flower blooming, the universe expanding. Imagine time as the canvas on which the universe paints its ever-changing masterpiece. As we begin to draw our shared voyage to a pausano, an end, but a quiet resting place for our thoughts stake, a deep breath, and feel the vastness of the universe stretching out all around us. Imagine the stars twinkling softly, distant suns sending their ancient light across the cosmos, each one carrying whispers of moments long past, yet alive for us here and now. Thanks for being here with me, floating through the cosmic sea where time flows in mysterious, wondrous ways. It's a gift to share this calm, curious journey. With you, your presence brings warmth to the cold, quiet darkness of space. If you like listening to quiet stories about space and stars, please tap the like button. It helps others find this peaceful place too. And if you want to come back for more calm journeys through the universe, please like and subscribe. Enjoy what I do here, and let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Feel how, though time stretches and bends around us, it also connects us all, from the earliest flicker of the first star to the ticking of your own heartbeat. Time is a river we all float on, sometimes rushing, sometimes slowing, always carrying the moments that make up our lives. Imagine that even in the stillness beyond time, there is potential, a space for new stories, new wonders, and new mysteries waiting to unfold. The universe is vast beyond measure, and time, though strange and elusive, is part of that grand tapestry, inviting us to explore, imagine, and dream. As we slowly drift back toward our own place and moment, carry with you the sense of awe and calm that comes from knowing we're part of something so immense, so timeless. Let that feeling settle like stardust within you, a quiet reminder that no matter where we are or when, we share this journey through space and time. Thank you for traveling with me, for your curiosity, and for your company in this quiet corner of the cosmos. Whenever you're ready, the universe will be here, waiting with more stories to tell, more secrets to reveal, and more moments to share. Until then, may your time be filled with wonder, peace, and the gentle magic of stars.